Welcome, everybody. Thank you for coming to today's seminar. It's a great pleasure to have here Professor Weiss from Vanderbilt University. Dr. currently an associate professor in the electrical engineering department and physics at Vanderbilt, and she's also the deputy director for the VINSE, I like this word, which is Vanderbilt Institute for Nanoscale Science and Engineering. She got her PhD from the Institute of Optics at University of Rochester, and she's been also a recipient of a PECASE, or Presidential Early Career Award, as well as an NSF CAREER Award, and an ARO Young Investigator Award. She was also recently named the Chancellor Fellow at Vanderbilt. Her broad research area of interest is in the area of photonics, optoelectronics, nanoscience, and technology, all the buzzwords that you can think of, which are very important, by the way. And it's a pleasure to have her here, and thank you for coming. The floor is yours.
Yeah, I appreciate the introduction and the invitation to come and talk about some of the work my group is doing at Vanderbilt. I've enjoyed my day so far, learning about some of the things that you do here, and I'm looking forward to the rest of the afternoon. The title of my presentation gives you some flavor of what we're going to talk about. So we're going to talk about how to repurpose silicon that we've traditionally used for microelectronics for sensing applications, and we're going to sense with light. So just to step you through the next 45 minutes or so, I'll start by giving you my broad introduction to sensors and molecular detection. So what kinds of things do we want to detect? What are the existing technologies, and how can we improve upon those? Then kind of the meat of the presentation is this idea of light-matter interaction. So light is going to be our optical probe. Matter is going to be the molecules that you want to detect. And it turns out the sensitivity and efficiency of your sensor has a lot to do with spatial and temporal overlap between where your molecules are and where your light is. And so there's two approaches for optimizing this light-matter interaction. The first one is to increase the light. You want to localize the light, increase the electric field. And the second one is to increase the number of molecules. So that's your molecular density. How can you make sure the molecules are where they're supposed to be and increase the number? And then finally, I'll end the talk by giving several examples of the kinds of things that we have detected in my lab. So before I get into that presentation, I thought I'd give you a broader picture of what my group does at Vanderbilt. So today's talk is over in this upper left quadrant of chem biosensing. Silicon's a subset. I also do some work with surface-enhanced Raman scattering with nanoporous gold substrates. We use similar structures that I'll be talking about today for optical computing, meaning that we're trying to enhance the efficiency of electronics by using light as the carrier of information, and modulating. You can essentially think of doing signal processing with ones and zeros. So light on, digital 1, light off, digital 0. So how can you go between states? We're doing that on a silicon platform, and our active switch is incorporation of a material called vanadium dioxide that can switch its properties at sub-picosecond time scales. So we're trying to push towards terahertz optical signal modulation. At Vanderbilt, we also have really strong presence in the radiation effects community. We have sources of X-rays, gamma rays, protons available on campus, and there's a lot of work going into studying especially the microelectronics for the future. So right now, as you launch things up into space, you're usually using microelectronics that are a few generations old because they've been proven radiation hard, and so this group is really pushing the envelope of what you can make radiation hard in terms of emerging technologies. And so since we had these sources available at Vanderbilt, some of my group has explored what do the presence of radiation do to materials. So this is a porous silicon material we'll be talking about. We've looked at colloidal quantum dots for future integrated devices, as well as some of the same photonic crystals and ring resonators to see how their properties change. And then the last quadrant are some collaborative activities that we have going on in drug delivery. So my group's contribution is in terms of porous drug carriers. That's porous silicon, again, repurposed, that we can do some shape engineering on. And then we have a new area of composite materials where we, again, use porous silicon as a high matrix, high surface area matrix, and incorporate metal oxides for analog memory, and now we're pushing into energy storage. So that being said, I'll get back to the topic of the day, which is optical biosensing. So I have up here a snapshot of 3 different companies that have commercialized technology. The most popular one is from Biocor, Surface Plasmon Resonance Instrument. And so this is really often considered the gold standard for molecular detection. If you're not familiar with it, the idea is that you shine light through a prism, and at the base of the prism you have a gold film where you're going to couple into a plasmon. So this is a collective oscillation of electrons at the surface that's very sensitive to the dielectric environment. And so as you're flowing molecules, if they attach through some specificity to the gold surface, it changes the properties, and you can measure that by the light coming out of the prism. And so this has been well developed. It has pretty good sensitivity. You can see it's a relatively large footprint tool, though, so it has high power consumption, and you'll need a clinical environment for that. Then moving on to the other two, these are more emerging technologies that have come onto the landscape in the last 5 years or so. The one on the far right is called Genolite. This is based on silicon ring resonator technology. So the guy who started this used to be in the field of optical interconnects with silicon, and so he just repurposed the structure he had for sensors. And so light would come into a bus waveguide, interact with this ring, which is resonant, and so the light is resonant in the ring, and the properties of light are very sensitive to the dielectric environment. So again, if you land biomolecules on this ring, you'll change the intensity of transmission that comes through the output waveguide. And we'll talk in more detail how this works. But this has been now, this company emerged a few years ago. And then the last one is a company called Silicon Kinetics that came out of work from UCSD. And they're based on porous silicon with just thin film interference. So they have a thin film of porous silicon. Light hits it, reflects off of it, and based on the optical thickness, you'll get a fringe pattern. And so if you load this porous matrix with molecules, you change essentially the refractive index, and you'll see a shift in your output spectrum. So contrasting the two emerging technologies, you have one that goes by kind of very simple principles of simple light interference with a material, and the other one that's more of the high sophistication. You need lithography to fabricate this ring resonator, but the fundamentals of light interaction with matter are consistent in both cases. Are we happy with the lighting? Yeah. I mean, I was told I have to point to this one, and I'm sorry, I'm not. Yeah. So perhaps I'll try to point to both. Apparently, I need to point to this board so that people can see it on the recording. Okay, so moving from those sort of tabletop systems that require some utilities and infrastructure, really an emerging goal is to have portable devices for biosensing. So you need these to be compact. So the goals are listed here. Cost-effective, portable, small footprint. You want low analyte volume. So people often say a finger prick of blood if you're doing medical diagnostics on a blood sample. Fast response, ease of use. You don't want to have trained personnel. And so I put up the vision of a few different groups. In the upper left is Brian Cunningham's group out of UIUC, and they use a smartphone-based technology where they've built an adapter that goes on the back of the smartphone to do some spectroscopy. Below that is David Erickson's group. Oh, that's wrong affiliation. He's at Cornell, mechanical engineering at Cornell, and he also has a smartphone-based technology where they're actually doing nutrition analysis with a paper-based dipstick. And then I believe it's a colorimetric assay that they're using the camera on the smartphone to determine the output. And then the bottom one in the right-hand corner is put out by IBM. And this one's a little bit more complicated, but the idea is it's, again, a very small, compact footprint. And they're trying to integrate technologies that are already well-known and established. So they're combining things like the electronics, signal transduction. We've got microfluidics, different materials and sample processing. So things that individually are known, they want to, this is the vision, they haven't produced this yet, be able to put those together in a small footprint and be able to produce these cheaply and effectively. So these are the kind of things that people are moving to. What I'll talk about today, the existing footprint would be a larger one, but there's some promise of scaling down these technologies to integrate with smartphones. Smartphones being the goal because they're relatively ubiquitous in society today. So finally, in terms of the broader vision, I wanted to motivate, in case you're not familiar, of what kinds of things can you do with biosensors? What do you want to detect? And so the main areas would be things like medical diagnostics. If you're sick, you want to know what disease state, and obviously early detection is preeminent importance. So their sensitivity is very important. You want to detect things below a threshold at which you get very severe symptoms. Food safety. So in this case, you really want to have cheap devices so that you can have them maybe in line in a processing plant, and high throughput. You want to have rapid screening in a cheap application. Environmental monitoring, so clean water, things like this, and finally homeland security, so toxins and explosives and things like that. So the typical classes of materials that we'll be looking at are DNA, proteins, viruses, and explosives. So these are all relatively small things to detect, and you'll see why small is important for us. So finally, in my last biosensing primer slide, if you're not familiar with what are called label-free biosensors, I want to just make sure everybody is on the same page before we start talking about the details of the data. So if you're creating a biosensor, you start with some functionalized sensor platform. So here I've labeled a substrate, and this substrate may not be playing a role, or it may be guiding light. But you have some substrate. Then you'll need some chemical linker molecules that link the substrate material to your probe or your bioreceptor. And these molecules on the top are very important for specificity. So for sensing, you usually have a particular type of molecule you want to detect. So if it's food safety, maybe you want to detect E. coli. If it's some disease state, maybe you're looking for a protein biomarker. And so you need to be selective to capture that out of the analyte solution that you're testing. And so the chemists or the biochemists have already established a lot of these bioreceptors. So you just need to figure out how to put that on your sensor surface. So once you've done this, this is the real starting platform. Then you expose your sensor to your analyte solution, which hopefully has your target molecule that you're trying to detect, but might also have some contaminants or interference in it. And so if everything is working correctly, your probe molecules or your bioreceptors will capture the target you're looking for, and then you need to rinse away everything else that's in the environment. Because depending on your metric of sensing, if you leave these other structures in the solution, you may influence your signal. So the rinsing step is also very important here at the end. Okay, so this is the one equation I wanted to show, and I'll step you through it and try to explain why it's important. What this equation is showing you is we're looking again at optical sensors. So we're going to look at a change in the optical spectrum that you want to measure. And so this omega-1 is what you can think of as the frequency of whatever the signature is in your spectrum that you're monitoring. And you want to see how much that changes when you expose it to your sample solution. So omega-0 is your initial frequency of that characteristic part of your spectrum. And then we have the integral. And in the integral, you've got your electric field intensity, and you've got the change in your dielectric function. And so the change in the dielectric function would be due to the presence of the molecules. So if we look at the first one, the electric field distribution, this one obviously is important in the sense that if you want to have a very strong signal change, so if you want omega-1 to be quite different than omega-0, you want strong fields. So the stronger the field, the more likely you are to have an easier shift in your spectral feature to detect. And so if we look at an example of waveguides, so waveguides are, if you're not familiar with waveguides, you can think of a fiber optic. Light, when you send it into a fiber, stays into the fiber. Here, when you send light into a planar ridge waveguide, it'll stay in the ridge waveguide. So in this color scheme, light is mostly focused in the center of this waveguide. And you can see the field distribution where, again, most of the light is in the center and just a little bit leaks out towards the surface. The middle, as I mentioned, this is the dielectric function. So this comes about when you add molecules to your surface. So initially, you would have an ambient that's air, or it's a buffer solution or a liquid. And then when you bring your molecules to the sensor surface, you've changed the dielectric environment. And so here, again, the importance of rinsing away, because if we leave these other contaminant molecules in the vicinity of the sensor, they can also increase this delta epsilon. And that isn't due to the presence of the molecule you want to detect. It's due to these other contaminants. So you need to rinse these away before taking your measurement. And then the final part is perhaps the most important one. And that's at the end of your integral, you have to consider the overlap, the volume. So you want to make sure that where you have your field and where you have your dielectric change are co-localized. Otherwise, your sensor is not going to work very well. So if you look at a traditional sensor in the optical regime, here's your substrate. So if the substrate is a waveguide, light is going to be focused in this substrate. So that's where your light is. And as I've shown schematically, here are your molecules. Here's where your dielectric change is going to happen. So you can see that these are spatially separated. This is not the ideal system. And if we look in terms of the actual field distribution, that means that the only region in which light is interacting with our molecules is this little evanescent field here on the surface. So most traditional sensors are working in this way, where you have relatively poor light matter interaction because you're relying on just simply changing the evanescent field where your light is and where your molecules are. And this is the same idea for surface plasma and resonance sensors. So it's a problem, it's a limitation, but yet the most popular sensor still works on a similar type mechanism. Okay, so if we now compare two of the platforms that I mentioned that have been commercialized, one is just thin film interference and the other one is a waveguide-based technology. I showed you a ring resonator. If you compare and contrast, you have the simplicity of interference. Basically, you have a thin film of material, you have, let's say, white light coming in, and based on the optical thickness, you'll have a preferred color that comes out. This is the same effect that you see if you spill oil on your driveway. If your car is leaking, you'll see a color spectrum, and each color corresponds to a different thickness. So your oil is a gradient in thickness, so each color corresponds to a different thickness. And so if you were to add molecules to the surface of this thin film, you change essentially the optical thickness of the film now, and so it's increased, and so you change the color that comes out, and you can monitor that change in color. So it's very simple, but you don't have very strong light matter interaction in the sense that you don't have a resonant structure. There's not a strong localization of field per se where the molecules are. And so if you look at the spectrum as well, you see these nice interference pattern, and you're going to be measuring a small shift in this interference pattern. On the other hand, if you look at an optical waveguide, this is more of a resonant structure. So if you look at a transmission spectrum, you'll have, and this is for a ring resonator, you'll have a very narrow resonance. And so for any small perturbation in this resonance wavelength, it's very easy to pick up because you get a very large intensity change. I'm sorry, I should be pointing here as well. The downside, so you do have strong light matter interaction inside the waveguide, but guess what? Your molecules are not inside the waveguide. This is the problem I mentioned of the integral with the DV. So you're only able to perturb the field a little bit by the presence of these molecules on the outside. So I'm going to talk about some ways to overcome this challenge. But first, I'll introduce three structures that are going to be the prototypical structures that we'll discuss today. The first one is called the photonic crystal. The photonic crystal is an engineered structure. So this is a silicon that's been lithographically structured to have air holes in it. And the presence of these air holes tells you a lot about where light can exist. So in semiconductors, we have electronic band gaps. So we know that electrons can't live in the band gap unless you have defects. The same thing in optics here. We have a photonic band gap. So where there's perfect periodicity with these holes, light can't exist here for a certain wavelength band. But you can see that there's a missing row of holes. And in that missing row of holes, light can actually exist. So this is treated as a waveguide. And it's a very efficient waveguide because if light tries to escape to the top or the bottom, it's unable to because, again, this photonic band gap. Then there's this small region here where we have three missing holes. And in this three missing holes, we can have a cavity region. So we have fewer holes here between the waveguide and the cavity. And so light with the proper characteristics, meaning the proper frequency or wavelength, can actually exist in this resonant cavity for some period of time. And so the strongest light is right here. And so if you put your molecules there, that's where you're going to have your strong light matter interaction. The second one I'll talk about is called this Bloch surface wave structure. And based on the periodicity of the multilayers, it turns out that this top layer is truncated a little bit and you get a surface wave. So now you've got your light that's actually localized right at the surface. And so now we have a stronger field that's in the surface as opposed to the bulk of the material. So we've helped our light matter interaction by shifting where the light is. And this grading on top is for coupling into that Bloch surface wave. And then the last one we have here is a ring resonator. And so in this structure, we've got what's called a straight or a bus waveguide, and next to it is this circular ring waveguide with a narrow gap between the two. And so in this case, light comes up, and it has two choices. It can either keep on going, so you'd have high intensity, or it can couple into the ring and be resonant in this ring, in which case you have very low intensity. And so in order to determine the coupling configuration, it's simple interference. So if the optical path length of light traveling around in this ring is an integer multiple of the wavelength, it will have constructive interference, and it will stay in the ring. When you look at the optical path length, it's based on the physical diameter of the ring as well as the refractive index. So now if you attach molecules on this ring, you've changed the optical path length and you change the coupling condition. So you, again, with very sharp resonant features, with a very small change in your refractive index here, you can go from a 1 to a 0 or some gradient there between. So these are very advantageous structures based on the light matter interaction. And as I show here, the highlighted. So for the Bloch surface wave, it's right at the surface of the structure. For photonic crystal, it's in this resonant cavity. And for the ring resonator, it's in the ring. I also wanted to give you some sense of, right now, what we need to measure these structures. So this is not your wearable portable device. This is, benchtop in the laboratory. So what we have is a tunable laser source that we're using that's fiber coupled that comes into the stage here. These are piezo actuators to get perfect alignment. We've got cameras up on top to kind of monitor what's going on. If you look at the monitor screen here, you're looking at a tapered fiber. So light comes in the fiber. This is tapered so that you can have very small spot sizes to couple into your waveguides. And then you have a mirror image on the other side where you have tapered fiber taking it out, and it goes either to an optical spectrum analyzer or a photodetector. So the system that we're using to test it is clearly benchtop. There's a lot of expensive hardware here. But as I'll show you, there's things that you can think about doing to the same system that will make it smaller and more affordable. And just to show you a little bit more zoomed in, if you haven't done silicon photonics measurements, this is a fairly standard setup. But if you look carefully, you can see that there's the fiber that's coming in here. So that's the input fiber. There's an output fiber to collect the light. This is the device under test. And there's a microscope objective coming above it so that you can see what you're doing. So that's shown here as well. OK, so this slide I wanted to talk about, OK, how can we improve our light matter interaction from the perspective of the electric field? How can we get more light where we want it? And there's a couple of different approaches. The most common one that people have done is called a slot waveguide. So I showed you this waveguide up here, which is a solid waveguide. Light is focused inside the center of the waveguide. But the problem is molecules are sitting on the outside of the waveguide. So if we introduce a narrow slot into the middle of the waveguide, it turns out that we can guide light in that narrow slot. So this is breaking the idea that traditional waveguide, your light is guided in a high refractive index material. It's confined by total internal reflection at an interface with a lower index material. Because we have a slot that's on the order of, let's say, 50 or 100 nanometers, boundary conditions to Maxwell's equations are the most important. And in terms of maintaining the tangential component of the electric field being continuous across an interface and the electric displacement being scaled by the relative permittivities on either side of the interface, it turns out that you get a big spike in the intensity of the electric field in the slot. And so that's shown here in this image. And now this slot, if it's an air slot, is accessible to molecules. So again, you're size limited, which is why we're looking at smaller size molecules. But if you can get the molecules into the slot, now you have very strong light matter interaction. You've increased your electric field, and you've actually increased the area available for molecules to access that region of the electric field. And so people have done this. This is not work from my group, but others, into the ring resonator platform that I showed you and made it a slot ring. So they can show improved sensitivities simply by adding that slot to the same ring resonator that you had before. So they showed, I think that's a factor of 3 or 4 improvement in the sensitivity simply by adding the slot. Another thing that my group has done is, in terms of the two-dimensional photonic crystal, is we've introduced something that we call multiple hole defects. So as I mentioned, for the two-dimensional photonic crystal platform, most of the light would be localized in the defect where we have 3 missing holes. And so we know the field is here, but if we've just simply removed the holes, we have a flat surface. And so we have that issue that molecules are on the surface, but most of the field is in the substrate of the material. And so by introducing these small holes, it turns out that we can engage that slot effect. So we actually can squeeze light into these smaller holes, again, based on boundary conditions and Maxwell's equations. So we can have strong field, and now we also have enhanced surface area. So the limitation, again, is small molecules. You have to be able to get them into small regions. But if you can see strong improvements. And I'll show you some actual data from our structures on that. And the last structure I'll introduce is also a slotted structure. This is called a one-dimensional photonic crystal, or a photonic crystal nanobeam. And what we've done here is we've created a cavity out of these holes. So there's a slight gradient in the shape of the holes and the diameter of the holes. And we've also put a narrow slot in it. And so this slot is about 50 nanometers. And again, I'll show you some more details later, but we can squeeze light into very, very small regions. And if you deliver molecules to those small regions inside the slot, you're going to get much, much higher sensitivity than you would in the original device. OK, so I'll say a few more words about the photonic crystal with the multiple hole defect. So here's the schematic of the structure. So this is the 3 missing holes, and here we introduce back our little tiny holes. And so if you look at the field distributions, they're very similar. So the field is strongest in where the holes used to be, the lattice holes used to be that we took out. And that's the same case with or without the defect holes. But if you look very carefully with the defect holes, you actually get regions where you have black here, where you have very, very strong field intensity. And the profiles are very similar. So you really don't perturb the optical quality of the structure, but you can localize and enhance the surface area and increase the fields. So if we look at one of our early results on the sensing, these are different resonance shifts based on adding different materials to the photonic crystal sensor without holes and with the defect holes. And you can see 2 things. So the first is the quality factor of this resonance increases by actually adding these defect holes. So clearly scattering is not a problem. We haven't had a lot of losses. We've actually had gains, and it's because of this slot waveguide effect. And then the magnitude of the shifts is larger because we've improved the light matter interaction. So we are detecting things that are small enough here that can get inside the holes. So we see a much bigger change in our spectrum. So that's important for a couple of reasons. The narrowness makes it easier to detect small shifts. And because the shifts are bigger for detecting the same number of molecules, that means that your limited detection goes down. So again, for medical diagnostic applications, if you're looking for the presence of certain disease biomarkers, you would like to catch that at the earliest stage possible, cancer being an example. You want to detect that before you have a very high level in your blood, because once you have the high level, you're probably already exhibiting other symptoms that tell you something is wrong. So one other very interesting thing when you're looking at light and electric fields is you have to pay attention to the field distributions. And so when we were first making the structure with the multi-hole defects, we had to decide where to put our little holes. Now you might say, well, why don't you just center them where the old holes were? And well, actually, that probably would have gotten you really close to the optimal solution. So we decided to do a more robust experiment. And we changed the spacing of the holes very gradually and determined how that changed the profile. So in the black, what you see is the resonance position, and in the blue is the quality factor. And the trend actually goes such that when you put the small holes exactly centered in the middle of the high field regions, you kind of hide the holes so that they don't scatter light, but yet you can squeeze light into those holes, and that gives you this very high quality factor. It also gives you, so the baseline of the resonance wavelength before having any of these defect holes would have been up here somewhere. I don't remember the wavelength, but it was much higher than 1530. And so actually the largest deviation is down here, which corresponds to where your quality factor is the highest. So there's certainly an optimal position. You have to do a little bit of smart engineering on your design. And if we look at a slice of the electric field right through one of these defect holes, you see this very sharp localization of the field, which is the same kind of thing that we saw for the slot waveguide effect. Okay, this is the second structure that I mentioned on the 2 previous slides, which I called the photonic crystal nanobeam. This we also coined in my group the term pinch waveguide, because we can actually pinch the field into very small, what we call mode volumes, a small spatial location. In this case, again, we've got this narrow slot running between these holes. And if you look at the field distribution or the power profile, you can see that we have very, very small localization where the field is very, very strong. So again, this is a really advantageous platform for if you deliver molecules to this region. And again, that's a little bit of a challenge, that you're limited into where you really want to get the most bang for your buck to deliver the molecules. If you can put them here, you get a large enhancement in your sensitivity. I think I'll skip this in the interest of time. So this is the fabricated structure. It's a little bit fancy in the sense that we've actually undercut it. So this is a suspended photonic crystal nanobeam. It increases the quality factor when you have symmetry in the dielectric function above and below your silicon waveguide. So when these are fabricated, there's an oxide underneath it. So this is on a silicon on insulator waveguide, which means it has about a 220 nanometer layer of silicon, then below it a couple of microns of silicon dioxide. And so if you remove the silicon dioxide by a wet etch process, you've got a suspended cavity, which increases the quality factor. And you can see the very, very sharp, narrow resonances that we're able to get from this structure. And this one, we're using a grating coupler. So we can couple light in through a grating. So you basically shine light from above. It couples into the waveguide, interacts with the pinch waveguide, and then couples out again from another grating. So you can do diagnostic measurements on chip with just having light sources measured from the vertical direction. Okay, so those were examples of how you can improve your silicon photonic sensors by really focusing on the design in terms of enhancing electric field. So the other side of light-matter interaction is the matter. So we wanted to look at approaches that we can increase the number of molecules that are present in the regions where our field exists. And so kind of the simplest, obvious one is this one shown here. So this is a ring resonator, and we simply did what we did for the pinch waveguide. We suspended it. So now molecules not only can land on the top of this ring, but now we've undercut the oxide away so they can land on the bottom of the ring. So we get a factor of 2 enhancement kind of for free. This is another interesting structure from the point of view of optomechanics, because now it's not quite as stable, and you can actually do very interesting things. If you have high fields passing through, you can actually change the mechanical motions and resonances, but that's a story for another day. The other area that my group has done a lot of work in is porous materials. So this is a top-down SEM image of porous silicon. And so now, instead of having just a solid surface where we're attaching molecules just on top of it, and again, the fields are stuck in the middle of the bulk of the material, if we porosify this material, we create little void spaces or little holes where we can pour the molecules into. So now you go from a flat surface area of attaching a few molecules to a volume where you can really capture a lot of molecules. And so again, by increasing the refractive index change from all these molecules entering, you get a much larger output response of your sensor. In terms of this porous material, we have 2 options for our surface chemistry. So if you remember back to the 101 slide, we have to functionalize our sensor with these probe molecules or receptors who are sensitive to and very selective at capturing just what we want to capture. And so the first option is you buy whichever your probe is that you want, and you just drop it on your surface. So that's kind of the standard route. That's what almost everybody is doing. We've also found that in these small nanoscale pores, because you're size restricted, you can get steric hindrance. So we worked a lot with DNA molecules. So if you look at the short axis of a strand, that's very easy to get in the pores. But if it flips the other way and binds on the side of the pore, you can actually get blocking if these are oriented horizontally. So we worked with some collaborators at Vanderbilt and found a way to synthesize our probes in situ. And so basically, base by base, we are growing our probe molecules inside the pores. And so we have much higher surface coverage, which means we can capture that many more molecules. And just as a side note, it's possible to use DNA to capture things other than the complementary strand of DNA. These are called DNA aptamers. So there's been a lot of studies in terms of the conformality of these strands, and it turns out that people, through what I would call kind of a shotgun approach, have figured out which sequences of DNA are good at capturing which other kinds of molecules, be they small molecules or proteins or other things. So I'll show you an example of toxin detection with DNA in a moment. In terms of the broad picture of why porous materials, surface area is the biggest reason why you want to do that. Instead of just having your molecules sitting on the surface, you now bring them inside your material. So light is guided in the bulk of the material, and so now it has strong overlap with your molecules, and you actually have more molecules present. So this is a really big reason why to look at porous materials. But from the practical perspective, you also get 2 added benefits. The first one is called pre-concentration of molecules. So for a lot of sensor applications, if you have just a few molecules diffuse in your environment, in order for your sensor to work, those molecules have to find their way to the sensor surface. And so you can have the most sensitive sensor in the world with a small surface area, and you might have to wait hours, days, years if you have a very low analyte concentration for that one molecule to land on your sensor. When it lands there, you can detect it, but good luck getting it to find your sensor. So a lot of actually sensors that are very sensitive but have limited surface area use a pre-concentrating porous filter. So they use the filter to capture these molecules out of the environment, and then they'll just rinse them off to make sure that they find the sensor surface. But if you have your sensor that's based on porous material, you can do the pre-concentration and detection in the same platform. And then the last one is size-selective detection, so filtering of contaminant molecules. By nature of the light being in the middle of the structure where your molecules are, even if you have some larger molecules sitting on the surface, you're not very sensitive and getting false positive results from their presence. So you can filter out, again, we're looking for detecting small molecules. The presence of the large molecules, we're much more immune to that than a sensor that is entirely based on surface detection. Just to give you an order of magnitude of the increase in surface area, I like to give this example. So if you take a planar sensor, and I've just given a 3-centimeter cube because it's about the size of a golf ball. So if you have a golf ball, that's your traditional silicon photonic sensor, and you're able to use the entire surface area, you have about 54 centimeters squared surface area for active detection. If you take that golf ball and now you porosify it with nanoscale pores, you can unfold that golf ball and it will cover an entire football field. So you have a choice. Do you want to capture molecules on a football field or a little golf ball sitting on the football field? So again, for small molecules that can get into the pores, you have a tremendous increase in surface area and impact on the performance of your sensor. For a very simple, but I think high impact slide here, what we did is we looked at a planar sensor and a porous sensor and attached just, we consider this a small molecule of aminosilane that's about a nanometer in size. So we attach it, it forms in a self-assembled monolayer, and we look at the response. And in this case, it's an angular dependent response. So we're looking at a silicon on-insulator waveguide that's just surface-based detection versus a pore silicon waveguide that's volume-based detection. And so for that monolayer attachment, you have almost no shift at all for the surface-based detection, but you have a very easily measurable shift for the porous sensor. And again, we can look at the field distributions in this case. For the planar sensor, your field is localized inside this gray area here. Your molecules are sitting on the outside. For the porous sensor, your field is much more distributed through the pores and also in the region above. So you're essentially able to use all this area as active sensing area. So the light-matter interaction is improved. Okay, so just a little bit of background about porous silicon. It's a very versatile material. If you remember from my early slide about introducing my group, we've used it actually for a lot of different application areas. A very positive aspect of it is it's very simple to fabricate, and you can control the pore size very easily. So you can tune the pore size very readily with the types of materials we're using from 10 to 100 nanometers. You can extend that range if you want to. The thickness is controllable. This is an electrochemical process, so it's based in HF, so hydrofluoric acid is a little bit nasty to work with, but by controlling the concentration of the HF and the time of your duration of your etch, you can control the thickness and the refractive index of your material. So you can essentially think of anything people would do with thin film optics where you're depositing layers of material, making reflectors and filters. You can do that in porous silicon by selectively removing and tuning the refractive index. In this SEM image here, I show two different layers. So the top layer has a higher refractive index, and the bottom layer has a lower refractive index. So the darker regions are air, and the brighter regions are the silicon matrix. So that top layer has more silicon proportionately, and the bottom layer has more air. In terms of how light interacts with the material, these are nanoscale pores, 10 to 100 nanometers. If we're using visible light, that's 400 to 700 nanometers. Most of the time, we're actually working in the near IR to lower the losses. Silicon's band gap is around 1,100 nanometers. So if we have 1,500 nanometer wavelength of light, it can't squeeze through a 50 nanometer pore. That can't happen. But you treat it as an effective medium. You have an array of these 50 nanometer pores, and so light actually can pass through this array of pores. And the refractive index of the material is then a weighted function between what volume fraction is air and what volume fraction is your silicon matrix. And so there's several different effective medium approximations you can use, and you just choose one for the geometry and morphology of your material. But you can see the trend is obvious. So at low porosity, that means low volume fraction of air, you have a high refractive index. In this case, this is porous silicon, so this is the refractive index of silicon in the near IR. And then as you increase the volume fraction of your air, you get lower and lower indexes because you're fractionally weighing the refractive index of air more, which is 1. So if you were to have 100% porosity, that would just be air, and so you recover the refractive index of 1. So by controlling the porosity, you have a very large dynamic range of refractive indices that you can achieve. And again, this isn't a uniform material, so you don't have to worry about lattice matching or anything else when you're doing depositions of materials. For sensing applications, we utilize the air regions to put our molecules. So now you have a 3-part effective medium. So when you introduce this additional material, it increases the refractive index of what used to be your air component. And so you would therefore be moving upward along this trajectory to higher refractive indexes. So when molecules are added to porous silicon, you increase the refractive index. So now I'll show a slide of structured porous silicon. So actually in my opening slide are the kinds of structures that have strong light matter interaction. if you look really carefully, that ring that I showed is the same one here. It's actually a porous silicon ring resonator. We fabricated this in porous silicon, so you can see the pores here from the top view and also from the cross-sectional view. What's really interesting is that we can get quality factors upwards of 10,000 in these porous silicon rings, which surprised me, actually, when my student reported the results. We thought the scattering losses were going to be much higher. So we're still a factor of 5 to maybe 10 below what you could achieve in silicon on insulator waveguides, but a Q of 10,000 is really quite respectable in terms of how much light you can localize into the ring. The upper left is a standard waveguide. So this is a grating coupled waveguide. The upper region has the high refractive index. The lower region has the low refractive index, so light's confined by total internal reflection. And then the bottom structure is the same one I showed on the opening slide of a Bloch surface wave. So here, instead of depositing materials to form your multilayer, we just selectively etch away different porosities to create our profile that's desired. So these are all top-down lithography we can do with electron beam lithography, or we could do it with photolithography depending on the feature size. But we can also do something kind of clever with porous silicon. With porous silicon, it's very easy to control the pattern in the vertical direction just by controlling the applied current density and the duration of the etch. But it turns out that we can do something pretty clever that soft lithography does. And we can actually take a stamp that we fabricate. In our case, it's a silicon stamp. Here I'm showing just an example of a grating. And without any photoresist layer or any polymer, we can directly press the stamp into a porous material, release it, and the porous silicon will conform to that pattern. So you can locally crush the material and form now laterally patterned porous silicon materials. And we can actually do this with surprising fidelity. So this has been done with features down below 100 nanometers. So we're essentially restricted by just the pore diameter, because for the operation of most of these devices, you need to have at least a few pores present. And so this kind of thing we've shown for diffraction-based biosensors in porous silicon. We've also used it for our Cirrus platform in gold that I haven't talked about. Okay, so if we want to do an apples-to-apples comparison to say, okay, how much do we gain by putting more molecules in the structure using porous silicon as opposed to planar silicon? Here's our bake-off, so to speak. So on the left, you have a porous silicon ring resonator, 10 micron. I think this was a 10 micron radius. And then silicon on insulator ring resonator that is the same 10 micron ring. These are functionalized for nucleic acid detection. If you look at bulk sensitivity, figure not shown, here we just introduced different saltwater concentrations to determine what the resonance shift was per refractive index unit of change in your solution. So the silicon on insulator ring was about 100 nanometers per refractive index unit. The porous silicon ring is about a factor of 4 better. So that's for just volume infiltration of a solution. But where the surface area really shines is in terms of molecular attachment. So here you are very limited in your surface attachment to the SOI, the silicon on insulator, whereas for the porous silicon you access the volume. And in this case, if we look at the attachment of the probe molecule of DNA for the surface-based sensor, the silicon on insulator, 0.2 nanometers as opposed to more than 11 nanometers for the porous silicon ring. So you have a tremendous improvement. So you can see that obviously the x-axis here has to be a little bit different, but the resonance are very sharp for the porous silicon, and you get much larger shifts from molecular attachment than you do for the solid sample. And so the metric of sensitivity was 4 picometers per nanomolar for the porous silicon and 0.2 picometers per nanomolar for the silicon. So same structure, you porosify it, you get more molecules, and you also improve your light-matter interaction because now light is interacting directly with the molecules instead of the evanescent wave. Okay, so how to further improve the porous silicon was going back to this approach of the in-situ synthesis of your probe molecule. So we found that with the traditional methods of surface functionalization, you take your pre-synthesized molecule, you dump it in the pores, we actually had pretty low surface coverage. So we have a football field of area, and we're only using about 10% of it because we haven't efficiently infiltrated these molecules. If we synthesize our nucleic acid probe molecule base by base, we can get up to 50% surface coverage, which is actually too much. So if you are covering 50% of your surface, if the complementary molecule were to come in, you would have 100% of your surface consumed. And of course, there you have steric hindrances. It's actually too crowded. So you have to reduce a little bit of your surface coverage. But that means you have tunable surface coverage up to an optimal. And I'll show you that we examined this. So here's the idea. We use some surface chemistry to determine the density of our probe molecules. And you can see that for a particular concentration of this linker that determines where the molecules will start to grow, we were able to optimize the performance of our sensor. So schematically, what you'll see is that in the case that you don't control the surface chemistry, you get super high density, up to 50% of your surface with the nucleic acids. With the controlled surface chemistry, you can limit the density of your probes. And when you have your complementary species, you can get very, very high hybridization efficiencies in the case where you have lower surface coverage, where when you have high surface coverage, the steric hindrance actually inhibits you from utilizing all the probes that are there. So the bake-off here is for, we used a photonic crystal as our platform. And on the left side, we did this in-situ synthesized probe, which gives us higher density. On the right side, we had just the regular pre-synthesized probe that we put down as is. And in comparing them, you have about an 8x improvement. So you can see these are now actually on the same scale. All the resonance shifts you can see are going to be larger in the case of using the probe that's been synthesized on the sample as opposed to pre-synthesized. So that's about a factor of 8 improvement by just using this novel functionalization technique. So finally, I just want to end with a few examples of the kinds of materials that we've detected in my lab. So on the left here are the structures we talked about that are the sensors. And then on the right are the kinds of things that we've detected. So we've done a lot of work with nucleic acids, both DNA and PNA, peptide nucleic acid. Everybody's favorite benchmark is the biotin streptavidin pair, so we've done that as well. But then we've done some more interesting ones. A toxin that we used, a bacteriophage, which is a larger molecule we did in the Bloch surface wave configuration. And then the last one here is one that's actually in progress now, where we're detecting Herceptin, which is related to breast cancer. So just to give you an idea of the kind of spectra that we look at, this is actually pretty old data. Again, remembering how a biosensor works, here's a little pore. We have to functionalize it first to get our probe molecule. We expose it to the species. We wait some period of time for specific binding, and I'm not talking about it today, but we have done kinetics analysis to understand how long it takes to bind on planar surfaces versus highly porous surfaces, and then you rinse it away. And so this is an example just of a simple porous silicon waveguide that's grating coupled. So you have an initial position when you've just fabricated your porous silicon and you've thermally oxidized it. Then we have various linker molecules. As you recall, in order to get the probe molecule on the surface, you first have to have the right glue, so to speak. And so the nice thing about optical monitoring is you can say, okay, great, our first chemical molecule attached. It's there. We saw a shift. And we know the approximate refractive index of this silane. And so based on the magnitude of the shift, we can actually quantify. So in this case, we had above 90% surface coverage. This is perfect. This is the one we want to form in a monolayer. Then we had another linker. I'll spare you the name, a long chemical name. It's another glue, so to speak. This one was actually, as you might guess, a larger molecule because the resonance shift is larger. So for those of us who are not chemists, we can all kind of say, well, organic materials, about 1.5, 1.6 refractive index, they're all about the same. So if you think of these as having the same refractive index, the only explanation of the larger shift is due to the larger size of molecule, and indeed that's the case. And then we come in, and finally we're at this point of the left schematic. So we put our probe molecule. In this case, this is DNA. And so the interesting thing you note here is that DNA, this is a 16-base DNA, so it should be a pretty large molecule. And if you assume the refractive index is similar to the other ones, the only thing you can infer is actually you have rather few molecules. So this was not taking advantage of the in-situ synthesis, and this is about 10% surface coverage of the DNA in the pores. But because we have low surface coverage, we actually have very high hybridization efficiency. So when we come in with the target DNA, you can see the shift from the last linker to the probe and the probe to the target are about the same magnitude, which means that almost all of our probes are able to capture the complementary species. And so we've done nonspecific binding assays as well to expose it to a non-complementary DNA sequence. And we tend to get anywhere between 5-to-1 and 10-to-1 selectivity. Okay, the second example I wanted to show you is using a similar DNA sequence. This is, again, in a porous silicon waveguide structure, but now we're actually able to detect a toxin. And so this was ochratoxin A, which is a food stock contaminant, small molecule. And we didn't do it, but others determined which nucleic acid sequence would conform and bend and actually capture this small toxin. So it has a molecular weight here, as shown, it's relatively small. And we're able to see the shift when we functionalize it with the DNA and then we capture the toxin. I don't have the sensitivity here, but I think it was on the order of a micromolar, which apparently is actually quite relevant for food stock contamination. The last structure I wanted to talk about is the Bloch surface wave. And so I'll just mention it very quickly. Traditional Bloch surface waves, as I explained, have light focused at the surface of the structure. So here's your multilayer. Light would be localized right at the surface. We actually did something a little bit more fancy. Because we were making this out of a porous material, it seemed to be a waste if our light was only focused at the surface. So we did a little bit of structuring so that you have a nonlinear gradient in the multilayer. And we're actually able, from two different configurations, to localize light both at the surface. So that's this red peak in both curves. So that's your traditional Bloch surface wave. But we also structured it so you have peaks of the electric field that are within the multilayer. So in this structure, we can do large molecule sensing at the surface and small molecule sensing in the middle. And each of the peaks that we have can tell you whether your surface-based sensor is working or your volume-based sensor is working. So this is an example of a large bacteriophage that we're looking to detect. And so here are our Bloch surface wave at the surface, and here is from within the porous silicon multilayer. And you can see that the multilayer peak does not shift, but the Bloch surface wave does shift. So we know here we've only detected this large molecule. Whereas this graph here shows the smaller functionalization molecules, and both peaks shift because you're able to detect the presence on the surface and in the volume. Let me just summarize. The theme of today's talk was silicon photonic biosensors, how to make them better, and the key is light-matter interaction. So you can either increase the electric field strength, or you can increase the number of molecules. So sub-wavelength features help you increase the electric field. Porous materials and this novel method of in-situ synthesizing your probe molecules helps you with your molecular density. So we looked at a lot of examples of different structures, and also what I commented on but didn't show data is it turns out that these can all be done in effectively real time. So on the order of minutes, you can get a response, and sometimes faster. Some acknowledgments. Funding was primarily from Army Research Office as well as the National Science Foundation. Fabrication was done both in-house at facilities at Vanderbilt called VINSE, as well as Oak Ridge National Laboratory and their user facility, CNMS. Several of my group members collaborated on these projects, along with some internal and external collaborators as well. So the last thing I wanted to do is a little sales pitch for any of you who are graduating soon or finishing up a postdoc. Vanderbilt is much smaller than NC State, but we're hiring. So probably everybody in the audience would map to one of these programs. Our ChemE program, which I'm on the search committee, is looking for nanoscale materials and energy. Mechanical engineering, similar search, nanomaterials and energy. Chemistry is looking for people at the interface of nanoscale materials. BME is looking for actually people who will synergize the medical center, and engineering and computer science is looking at big data and cyber physical systems. So if you have any interest, please take a look, because we have a new building that's going up. We've got a lot of space, growth opportunities. So if you're interested, I've been happy at Vanderbilt, so I think it's a great place to work. So that ends my sales pitch.
We have time for a few questions.
Very nice presentation. I have a quick question. These sensors that you're developing, are they reusable? Are they one time, and can you make them reusable?
Yeah, so that's a good question. They are reusable. So there's different ways that you can reuse them, in the sense of if you have a DNA sensor, you can simply denature. And so your probe will remain on the surface, but your target molecule, which was only attached based on the interaction of the binding of the nucleic acids, you heat it up above its melting point, it'll denature, you can wash it away and reuse it. So we've reused our sensors multiple times with that approach. You can also, from the surface chemistry perspective, so our ring resonators, so these are structures that we lithographically fabricate, so we have a limited number. Porous silicon's easy, we can just make those all the time in the lab. So the lithographic ones, if we go to Oak Ridge, we only go every so often, so those we want to reuse. Those we tend to just soak in piranha, and so there you can wipe off your surface chemistry and just start again. So the base of your structure, which is the silicon photonic structure, can be reused. In terms of whether you want to reuse them, it probably depends on your application. So from my understanding, for a lot of health applications, you probably don't want to reuse them just on the nature of human samples and that sort of thing. So there is a drive to have these cheap enough that they could be disposable.
Any other question?
A couple of minutes is the speed in which you can get a result with the equipment you have now. Has any work been done putting this into a context of like a medical application, where from gathering the sample to getting the final result actually presented to the technician or the scientist?
Yeah, so that's a good question. When I say a few minutes, that's our purified sample that we're putting on the structure, and we're measuring the binding kinetics. And so you can already get a signal very quickly. Usually the saturation is about an hour. In terms of if you were to extract that sample from a person, this is an area of research we're just moving into. So if you can actually operate in serum or in blood, then it's actually pretty fast to take the sample, obtain it from the person, drop it on the sensor, and measure it. And so based on some other results published in the literature and some of our preliminary results, it looks like we probably are going to be able to do that, in which case your sample processing is pretty minimal. So that means that your overall response is still very fast.
Any other question? Yes, Dan.
For your suspended waveguides, is there an issue with microphonics or mechanical resonances or vibrations?
Yeah, so that's an excellent question. And so with every challenge, there's an opportunity. So my group is now looking into the area of optomechanics, because if you get very, very strong field concentrations, you can actually introduce these resonant modes. Or at the same time, just like microcantilevers, if you put big things on top of it, it's going to create a vibration. And when you're relying on a constant optical path through it, if you've got these vibrations, it will impact it. So that is a potential limitation. Or you can repurpose it and try to take advantage of that additional degree of freedom. Yep.
Following on that question, how complicated is the task of taking advantage of that mechanism? Like, how much complexity does it add to the device or to your computations in order to make sure that you get the...
So I would say, in terms of making them, it's a minimal extra step. Basically, you have a large area lithography to open a window where you're going to put your buffered oxide etch to wet etch it. The complexity really comes into the design and the yield, because you have to make sure that you're still mechanically robust. So you want to try to minimize, in this case, the vibrations, and you don't want if you put this in a microfluidic channel with flow going against it, you don't want it to either vibrate or break. And so we've had different designs that we've looked at, and if I just pull up my title slide that I know has one. So, I've lost it. There we go. So if we look at this configuration, you can see that we've got these little tethers. And so this is what's holding us together. And so there's sort of a trade-off. The fewer tethers you have, the better the optical quality of the structure, but then the less robust it is. So we found that 3 tethers is actually robust to reusability. 2 tethers, not so good. So there's a trade-off there.
Yes,
your porous silicon direct printing or imprinting of porous silicon is pretty interesting. Mm-hmm. Was that a very easy process to develop, or how did you make that?
Yeah, so my graduate student thought that he could do this, and I said, no, that's not going to work. You're going to just crush the whole film. So he said, okay, I'm going to prove you wrong. So we had silicon gratings that were in the lab. He took the vice grip, and he pressed it together. You shine a laser pointer on it, and you see a diffraction pattern. So, I mean, it works. So what we've done to refine the technique is, obviously, if you want to do nanoscale imprinting, we've worked on planarity to make sure we have uniform pressure across a surface. We've also done things like non-stick coating to make sure that your stamp doesn't stick and rip off the porous silicon or the nanoporous gold we've used it in. But it's really a very straightforward process. We've extended it to grayscale lithography. So if your stamp is now, we've done bowl shapes and curvilinear geometries, so you can imprint those directly in porous silicon. So it's actually quite versatile, very simple, and we don't have to deal with pattern transfer. It's just a direct process, room temperature, room pressure, and literally it takes just a few seconds to do.
This would be the last question. Just to pick up on that very question, it seems like you have it, there's a calibration process that if you were to use it as a sensor, ultimately you're going to have a calibration process to basically match whatever light comes in and how it's affected, as well as the porosity, density, if you will, of the material. How complicated is that?
So it's actually relatively straightforward to calibrate in terms of, so we have calibration curves of what applied current will give you what refractive index, how long gives you what thickness, and once you know the profile, it's a very simple transfer matrix method. Approximations work quite well in terms of determining the profile of your structure and how light interacts. So it may not be as complicated as you think. If you want to get very rigorous estimates, I think you can look into the finer points, but to get a ballpark analysis, it's actually not too challenging.